Picture this. You're living in Cashion, Oklahoma. It's springtime, the birds are chirping, and you just had this brand new state-of-the-art heat pump installed at your house.
Oh, yeah. You're probably feeling pretty fantastic about that.
Exactly. You're ready for like top-tier home energy efficiency. You're ready to see those utility bills just absolutely plummet.
Right, which is the whole point of getting one.
Right. So summer goes by smoothly, fall rolls around, your October electric bill arrives in the mail, and, it's a perfectly reasonable $110.
Yeah, totally normal.
Then November drops, and it's $145, which, makes complete sense. The weather's getting a bit chillier, you're running the heat a bit more.
Sure, you expect a little bump.
But then December hits. You go to the mailbox, you tear open that envelope, and your jaw just hits the driveway. It is a whopping $380.
Ouch. Yeah, that hurts.
Right. So you immediately pick up the phone, completely furious, and you're calling your installer because, obviously, you are absolutely convinced this expensive, brand new piece of machinery is completely broken.
It is, it's a classic homeowner horror story. But the wild twist here is that the system isn't broken at all.
Wait, really?
Yeah, not at all. That $380 bill is actually the result of a machine doing precisely what it was designed, manufactured, and, programmed to do.
Okay, let's unpack this right out of the gate. Because if I am that homeowner, I am really struggling to understand how a machine designed specifically for efficiency can triple my bill in a single month.
Oh, I totally get that. It sounds completely counterintuitive.
Yeah. Like, if it's not a physical breakdown of the equipment, are we looking at some kind of fundamental design flaw with heat pumps? Or is this an operation flaw?
Well, we are looking at a massive communication and operation flaw.
Yeah.
And honestly, that's our mission for this deep dive.
Awesome. Where do we even start?
By synthesizing Department of Energy guidance, Energy Star data, and some incredibly detailed field notes from a master HVAC technician operating right there in Oklahoma. We're going to break down the actual mechanics of winter heating.
Okay.
We're going to reveal what this thing called auxiliary heat actually is, why your winter electric bills can just suddenly skyrocket, and most importantly, the 3 very specific thermostat settings that stand between you and a massive financial penalty.
I love this because this isn't just, academic theory. It's immediately actionable for anyone listening right now.
Exactly. You can go check your wall after this.
Right. But before we get into the mystery of why the bill spikes so violently, we really need to understand the baseline. Like, we need to understand how this machine normally operates when your bill is just that low, happy $110.
Yeah, building that foundation is key.
So how is a heat pump actually heating a house in the first place? Because honestly, the name heat pump almost feels like a misnomer once you actually look under the hood.
It really does. You kind of have to throw away your preconceptions of what a heater actually is. It helps to think of a heat pump not as a furnace, but simply as an air conditioner running in reverse.
An air conditioner running in reverse, okay.
So during the hot summer months, your AC uses a chemical refrigerant to absorb the warm air inside your house, carry that heat energy outside, and just release it into the yard.
Right, pretty standard stuff.
But in the winter, a heat pump utilizes this physical mechanism called a reversing valve. And that valve literally shifts the flow of the refrigerant. So now the system absorbs heat from the outdoor air, carries it inside, and releases it into your ductwork.
Which, frankly, always sounds a little bit like magic to me.
I mean, it is basically thermodynamic magic.
Because when it's January and it's freezing outside, my brain just insists there is no heat out there. It is cold.
Right. That's what your senses are telling you.
Yeah. But physically, scientifically, there is heat. I always like to think of the outdoor air like a slightly damp sponge. Even when that sponge feels completely dry to the touch to us and it's freezing cold, if you have a strong enough mechanical squeezer, you can still wring a few extra drops of water out of it.
That is a brilliant analogy. And the physics behind that sponge actually come down to absolute zero.
Oh, wow. Going deep into the science.
Yeah. Heat energy actually exists in the air all the way down to negative 459 degrees Fahrenheit.
That is insane.
So even when it is like negative 10 degrees outside in Oklahoma, there's still a massive amount of thermal energy just floating around in the air.
So the sponge is still plenty damp for the machine.
Exactly. Because the refrigerant inside the heat pump boils at an incredibly low temperature, it can easily absorb that ambient heat, compress it to increase its temperature, and push it right into your living room.
Right, but there has to be a physical limit to this, doesn't there? Because here's where it gets really interesting to me. As the outdoor air gets colder and colder, that metaphorical sponge is getting drier and drier.
Yes, exactly. The heat becomes sparser.
There's simply less heat available to grab per cycle. So at what point does the system just give up and ask for help? Because it can't just keep squeezing a nearly dry sponge forever without working itself to death, right?
No, it can't. The tipping point occurs as the temperature drops, and the compressor has to work increasingly harder just to extract that same amount of heat.
So you start noticing changes in how it runs.
Yeah, the system will run longer cycles. The air coming out of your vents might feel a bit lukewarm rather than blasting hot. And eventually, the machine simply cannot extract heat fast enough to match the heat your house is naturally losing through its windows and walls.
And that's when things change.
Right. When the heat pump realizes it is losing the battle to maintain whatever temperature you set on the wall, it basically calls in the cavalry.
And that cavalry is the exact culprit we are hunting today. We are moving from the incredibly clever, efficient heat pump sitting out in your yard to a component hiding inside the ductwork of your house.
Hiding is a good word for it. Most people don't even know it's there.
It's a component that the source material literally describes as a giant toaster. The HVAC industry calls it auxiliary heat, or O-heat for short.
Yeah, O-heat. And when you hear that term, you should really envision massive electric resistance heating strips.
So just literal metal coils getting hot.
Exactly. Literal metal coils that get glowing red hot. It is the exact same underlying technology as the coaster sitting on your kitchen counter or, a cheap electric space heater you might plug in under your desk, just scaled up massively to fit inside your central air handler.
Okay, so we have this giant toaster hiding in the attic or the basement. And the data lays out a few specific triggers for when this toaster actually turns on.
Right, there are rules it follows.
It kicks in when the heat pump just can't keep up with the cold, or when the outdoor temperature drops below a specific programmed balance point, or, and this is a huge one we'll get to, when there's a big jump in the thermostat setting.
Oh, that last one, because so many people.
But before we get to those triggers, we really need to understand the financial penalty. Why is this giant toaster so astronomically expensive to run compared to the heat pump outside?
Well, the financial difference comes down to a fundamental engineering metric. It's called the coefficient of performance, or COP.
COP. Okay.
Yeah, this is how the industry measures the efficiency of heating systems. A modern, high-quality heat pump running in relatively mild winter weather operates at a COP of roughly 3 to 4.
Meaning what, practically speaking? Like for the person actually paying the electric bill at the end of the month?
It means that for every 1 kilowatt of electricity you purchase from your utility company, the heat pump delivers 3 to 4 kilowatts of actual heat energy into your home.
Oh, wow. So you pay for one, you get 3 or 4 out.
Exactly. You pay for 1 unit of energy, and you get 3 or 4 units of heat out of the vents. It is a phenomenal return on investment because you are not creating heat from scratch. You're merely paying for the electrical energy required to move existing heat from the outside to the inside.
Okay, let's look at the other side of the equation then. Let's look at the giant toaster, the electric resistance strips of the O-heat.
Let's do it.
The data shows that O-heat has a COP of 1. Now, hold on. I have to push back on this for a second.
Sure, go ahead.
If I am looking at a 1-to-1 ratio, right, 1 kilowatt of electricity gives me 1 kilowatt of heat. To anyone walking down the street, 1-to-1 sounds perfectly efficient.
It does. It sounds great on paper.
It sounds like 100% efficiency.
Yeah.
Every drop of electricity I buy is being turned into heat. Nothing is being wasted up a chimney or whatever.
That's right.
So how on earth does a 1-to-1 COP translate to an electric bill that is suddenly 3 to 4 times higher for you, the listener?
It's a great question. The trap is that 100% efficient sounds flawless until you compare it directly against a machine operating at 300 or 400% efficiency.
Ah, right. It's all relative.
Exactly. Consider the fundamental difference in the mechanics. The electric strips are generating heat from absolutely nothing. They are forcing high-voltage electricity through a high-resistance wire to artificially create heat.
Like friction, almost.
Yep. That creation process is 1-to-1. But the heat pump is a mover, not a creator. Moving a heavy box across a room requires significantly less energy than building an entirely new box from raw materials.
Oh, that makes so much sense. So when the system gives up on the outdoor heat pump and switches over to the indoor O-heat, You instantly lose that magical 3 to 4 multiplier.
The mathematics of it are brutal, honestly. The moment those toaster strips engage, your heating system goes from costing you, let's say, 10 cents to deliver a specific amount of heat to immediately costing you 30 or 40 cents for that exact same amount of warmth.
Wow.
It is an instant, automatic, and totally invisible price hike. And that mathematical cliff is the exact reason our homeowner in Cashion opened a $380 bill. Their system spent hours every single day relying on the COP1 toaster instead of the COP3 heat pump.
So what does this all mean for our daily routines? Now that we understand what O-heat is and the severe financial penalty it carries, let's talk about self-sabotage.
My favorite topic. People do this to themselves all the time.
Because the data makes it painfully clear that a homeowner's own daily habits might be accidentally turning this giant toaster on without them even realizing it.
We really have to unlearn decades of conventional wisdom regarding how we heat our homes.
What do you mean?
Well, if you grew up in a house with a traditional gas furnace, you're almost certainly taught to utilize big thermostat setbacks. The standard practice is to turn the thermostat way down at night while everyone is sleeping under heavy blankets. Maybe you drop it down to 65 degrees.
Right, save some energy while you sleep.
Exactly. Then, when the alarm goes off in the morning, you bump it back up to 72 degrees. With a gas furnace, that strategy makes perfect sense, and it absolutely saves you fuel.
Right, because a gas furnace is basically a flamethrower.
Pretty much.
It blasts 100,000 BTUs of heat and can warm up a freezing house in a matter of minutes. But if you tried that exact same morning routine with a heat pump, wait, let me look at how this plays out.
It's a completely different ballgame.
If you drop the house to 65 at night and then ask the thermostat for 72 degrees at 7 a.m., that sudden call for a 7-degree recovery is a massive shock to the system, isn't it?
A massive shock. The data reveals that a request for a 7-degree jump basically forces the thermostat to panic.
It panics.
It does. It sees a massive temperature deficit, assumes you are freezing and want that heat instantly, and it immediately deploys the O-heat strips. Those electric coils might run for an hour or more just to quickly bridge that 7-degree gap.
Hold on. This feels like a massive betrayal by the very thermostat I paid for.
I know, it really feels that way.
Because the system data shows that the heat pump alone could have achieved that 7-degree jump. It might have taken, 30 or 40 minutes instead of 15, but it could have done it operating at a highly efficient COP of 3.5.
That's completely accurate.
So the thermostat is actively choosing a method that is 4 times more expensive just because I asked for a 7-degree bump. It feels like I'm being punished for trying to be energy efficient at night.
It is a harsh reality to discover that the algorithmic logic of your thermostat is actively working against your wallet. The standard programming of most thermostats prioritizes comfort and speed above all else.
Speed over efficiency.
Always. It assumes that if a human asks for 7 degrees all at once, the human wants it right this second. So it bypasses the slow, steady, highly efficient marathon runner, and it deploys the most powerful, most expensive sprinter it has in its arsenal.
So the lesson for anyone listening with a heat pump is incredibly simple. Stop touching the dial.
Yes. Hold the set point flat. Find a comfortable temperature for your home, say 68 or 70 degrees, and simply leave it there 24 hours a day, 7 days a week throughout the winter.
Just don't touch it.
Don't touch it. By not creating those massive recovery demands, the heat pump can just hum along at its highly efficient COP3. It maintains the temperature easily without ever feeling the need to panic and trigger those expensive toaster strips.
And the savings from that.
Maintaining a flat temperature actually saves heat pump owners 10 to 20% on their seasonal heating bills.
Okay, so that covers human behavior and our obsession with turning the heat down at night. But if human behavior is one trigger, the next logical question is what triggers the toaster when the homeowner hasn't touched the dial at all?
Which happens a lot.
Right. Let's say you are out of town, the thermostat is perfectly flat at 68 degrees, but that December bill still spikes. This brings us to the hidden installer settings deep inside the machine.
This is perhaps the most crucial technical element we need to explore today.
Yeah.
Every heat pump installation involves a critical configuration called the balance point.
Balance point.
Yes. This is a specific outdoor temperature threshold that's programmed into the thermostat. It basically acts as a strict gateway. It is the exact temperature at which the computer finally gives the O-heat permission to turn on and assist the heat pump.
Okay, and what does that usually set to?
Well, the manufacturer's default for this balance point is usually set quite high, typically around 35 to 40 degrees Fahrenheit.
Okay, let's walk through a practical scenario here. It's a brisk fall morning, and the outdoor temperature drops to 39 degrees. The factory default balance point is sitting there at 40.
Yep.
So the thermostat looks at the weather and says, hey, it's 39 degrees, we crossed the threshold, you now have permission to turn on the giant toaster.
And that permission is granted entirely regardless of whether the heat pump actually needed the help or not.
Oh.
The problem is that in relatively moderate climates, like central Oklahoma, a properly sized modern heat pump is incredibly robust. It can easily carry the entire heating load of a house all by itself down to 25 or 28 degrees without breaking a sweat.
So if I just let the installer leave it at the factory default of 40 degrees, it's basically like buying a high-performance sports car but leaving the emergency brake engaged for 80% of the winter.
That is exactly what it's like.
I have this incredible efficient machine outside that can comfortably handle 28 degrees, but the computer inside is forcing it to rely on the incredibly expensive backup strips anytime it drops below 40. That's nuts.
It is. By simply accessing the advanced installer menu and lowering that balance point from 40 degrees down to 28 degrees, a homeowner keeps those expensive strips completely disabled for 80% of the winter mornings they would have otherwise run.
That's a huge difference.
It is a massive financial swing, and it's based entirely on a single two-digit number.
But wait, why on earth would massive multi-billion-dollar manufacturers set the default so high if the machines can easily handle 28 degrees? Are they, like, secretly in cahoots with the local electric companies?
No, it's not a conspiracy. It really just comes down to corporate risk mitigation.
How so?
Manufacturers have to set a conservative default because when a unit rolls off the assembly line, they have absolutely no idea where it is being shipped.
As
A poorly insulated house in the harsh winds of Maine requires a vastly different balance point than a tightly sealed new build in Oklahoma. So the manufacturer sets it to a safe 40 degrees to guarantee that every single house gets warm incredibly fast.
So they don't get complaints.
Exactly.
Yeah.
They're actively avoiding angry customer service calls about chilly houses, even if that speed costs the homeowner a fortune in electricity.
Which perfectly highlights the value of the field notes we have for this deep dive from Dave Hartzell.
Oh, absolutely. Dave's data is gold.
The records specifically point to Dave, a professional with 45 years in the HVAC industry. He holds a master license, he is NATE certified, IGSHPA accredited. He runs Hartzell's Heat and Air out of Kingfisher, Oklahoma.
A real veteran of the trade.
And what does Dave do differently than the big box installers? He manually recalculates and programs this specific balance point on every single install he does. He drops down to 28 degrees, and then he actually sits down and explains the thermodynamics of it to the customer.
The inclusion of Dave's methodology reveals the sheer value of a highly experienced local expert.
It really does.
Dave intimately understands the specific climate data, the humidity, the wind patterns of central Oklahoma. He knows exactly where the thermodynamic tipping point is for the architecture in his specific region.
Pretty fine-tunes it.
Yes, he calibrates the machine so the customer actually receives the extreme efficiency they paid thousands of dollars for.
Right.
It is a vital configuration step that rushed, volume-based installers almost universally skip because it takes extra time and localized math.
Okay, so we have covered the automatic temperature triggers, we have covered the hidden balance point settings, and the importance of finding a local wizard like Dave.
Right.
Now we have to talk about the final, most direct, and frankly most tragic way homeowners intentionally spike their own electric bills. We are moving away from automation and looking at the manual override, the do not touch button on the front of the thermostat.
Ah, yes. We are entering the dangerous territory of emergency heat.
Yes. Let's talk about the psychological trap of emergency heat versus auxiliary heat. Because, let's be real, you wake up in the middle of January, you throw off the covers, and it is freezing in your house.
And you're miserable.
You walk over to the hallway thermostat, shivering, and you see a physical button clearly labeled emergency. The human brain immediately translates that word to, give me maximum heat right now, this is an emergency, I am cold.
Naturally.
It sounds like a turbo button on a video game controller.
It really does. The nomenclature is incredibly misleading. It sounds like a turbo button that will combine all the powers of your system into one massive blast of warmth.
But it's not.
Mechanically, it is the exact opposite of a turbo boost. Emergency heat is a manual, hardwired override switch. When you engage it, It sends a signal that completely locks the outdoor heat pump off.
Wait, it turns the good part off?
Completely. Yeah. It disables the highly efficient COP3 machine sitting in your yard entirely, and it forces the system to run only the extremely expensive COP1 electric heating strips in your ductwork.
Wait, so it doesn't even run them both together to get the house warmer faster?
No, it shuts down the efficient system completely. And the great irony is that it does not heat your house any faster than the heat pump and the O-heat working together normally would.
That is tragic.
It simply forces your home to rely on the absolute most expensive heat source, exclusively and indefinitely, until you manually turn the button off.
So you were telling us the emergency heat button is basically an I would like to set my money on fire today button?
In terms of your utility bill, yes.
Unbelievable.
The only time you should ever activate emergency heat is in a literal mechanical emergency. Like if the outdoor heat pump unit has physically been crushed by a falling oak tree.
Okay, an actual disaster.
Right. Or the fan motor has violently burned out and is smoking, and the unit is mechanically dead. Activating emergency heat is simply a desperate backup measure to keep your indoor plumbing from freezing solid while you huddle in a blanket and wait for someone like Dave Hartzell to show up in his repair van.
That is wild. The psychology of that button is so counterintuitive. And, it brings this whole journey full circle right back to that poor customer in Cashion, Oklahoma, staring at a $380 envelope.
Yep.
They didn't have a broken piece of equipment. They had a fundamental misunderstanding of the incredible technology sitting right there in their living room.
And if we pull all these threads together, the big picture for you listening is actually incredibly positive and empowering.
Good, we need some good news.
A heat pump will absolutely save you a significant amount of money compared to a traditional gas furnace for the vast majority of the fall, winter, and spring seasons.
Awesome.
The only exception is during those absolute bitter, coldest weeks of deep January. But if you apply the right daily strategy, meaning you abandon the old habit of massive nighttime temperature setbacks,
Leave the dial alone.
leave alone, and you ensure your local installer has carefully configured the correct balance point setting for your specific zip code, you can drastically minimize that inevitable heat penalty.
And stay away from the turbo button.
And whatever you do, do not touch the emergency heat button unless a physical tree has fallen on your unit.
So we've solved the mystery of the $380 bill and hopefully saved everyone listening a massive amount of money this winter. But I want to leave you, the listener, with a final lingering thought to mull over.
Oh, what's that?
Because looking at the mechanics of this really got me thinking about where home automation is headed. We have these incredibly smart thermostats on our walls now, right?
Right.
They connect to the Wi-Fi, they use algorithms to learn our daily schedules, they sense when we leave the house, they even check the local weather forecasts.
They do a lot.
So why on earth are we still relying on a human installer, even a master like Dave, to manually program a static, unchanging balance point number into the computer?
That is a very good question.
Shouldn't a truly smart ecosystem be able to dynamically adjust this balance point in real time? Imagine a thermostat that constantly checks the outdoor humidity, monitors your specific utility company's time of use electrical rates, measures the thermal mass of your living room, and calculates the exact real-time moment the heat pump's efficiency drops below the toasters.
That would be the dream.
It could adjust that balance point minute by minute, rather than forcing us to guess based on a fixed 28-degree rule of thumb.
That points directly to the massive gap between current smart home marketing brochures and actual applied thermodynamic optimization. The technology definitely exists, but the integration is still lagging way behind the physics.
Well, maybe the evolution of the dynamic smart grid is a topic for our next deep dive. But for today, we want to enthusiastically thank you for joining us as we unpacked the hidden mysteries of the heat pump. Go check your thermostat settings tonight. Make sure you aren't accidentally leaving the emergency brake on. And whatever you do, back away from that turbo button. We will catch you next time.